Sierra, somehow or other we've been forced to talk about biorhythms of the moon in retrograde or something.
Pluto is going to be in retrograde all month, and then for the rest of the
Andrew,
month,
what have I done?
Irrelevant. She's so here.
Okay, so here's the deal. These linear programming things are actually not awful. They're actually kind of a vaguely fun type of thing because basically, okay, making the graph is not some huge deal. You had some constraints, like y had to be positive. That means you're talking this area. X had to be positive, so you're really talking just the first quadrant. And then maybe x plus y had to be less than 10. So you got this requirement. So it's just this little bounded region. So like maybe in this case, this is your little region. In other words, for the set of requirements that you have, y had to be positive, x had to be positive, and x plus y had to be less than or equal to 10, you end up with this little bounded region. Any number in there would work. Here. Let's say right here. Let's say this point is 1, 1. That would work. 1 is greater than 0, 1 is greater than 0, and 1 plus 1 is less than 10. It's right. Yay! But then it says, let's say these two functions here, this is set of constraints, and we have some objective function z equals, let's say, 2x minus y. I don't know why it would be that, but let's just say. Okay? I don't know. Maybe that is the money you'll make based on selling X of this and Y of that. You know, X transistors and Y chips. Okay? So if you sold 3 transistors and 2 chips, how much money you'll make? Whatever. Well, the answer as to where is the maximum of the amount of money you would make will be at one of these 3 corners. Which happen in this case, I can do the math of this one in my head, to be at 0, 0, 0, 10, or 10, 0. I mean, if I plugged in, this is a perfectly good solution, 1, 1. It's a place inside of the feasible region. But, if we actually plug that in here, 2 times 1, if we actually plug that in at that place, z would be equal to 1, right? We plug 1, 1 into here, we get 2 minus 1 is 1. On the other hand, if we plug z into here, 0, 0, we'll get 0. If we plug z in over here for x is 1, we get negative 10. And if we plug it in over here, we get 10. So there is a best possible place where you know, the right number of x, or whatever they are, and y, whatever they are, it happens to be at that bottom corner there. Your best bet is to make 10 of whatever the x's are, and use none of the y's, which in this case kind of makes sense, right? I mean, you're actually losing money for every y you made. It made sense to make as many of these as possible, and none of these, but whatever. They would always be so obvious.
Yeah, and just like last night on the homework,
yes.
the minimums were like 0, 0, because that was like the
yeah, that might be. If the thing is to make the minimum, in this case, making the, like if you want to lose money for some reason, in this case it would be here. But if you're looking for a minimum, it's often the case that the minimum money to make is 0, 0, right? Donut Bank would make the least money today if they made no apple fritters and no glazed donuts, right? But there is a correct number of apple fritters and glazed donuts to make based on things like we have this much flour and we have this much sugar, okay, and this much apples, okay, what's the right amount? We make this much money on each glazed donut, and we make this much on each apple fritter. There is a correct, no, there's a large number of possible numbers of apple fritters. You can't make 1,000,000 apple fritters and negative 900,000 glazed donuts, right? That mathematically that would work. But, you know, it isn't like somehow they're making negative donuts puts more flour in the cabinet, right? You can't, there's a correct number, there are feasible solutions, which is what's going on today at Donut Bank, right? They made a feasible number of apple fritters and glazed donuts. They didn't run out of flour or anything like that, right? They didn't like have to go across the street and borrow flour or they ran out or something. But they also may or may not have made the maximum amount of money, right? Now, most businesses have at least software to do what we're about to do. If they were only making 2 products, you could actually do this the way we did in the class. if you run a lemonade stand and you're trying to figure out how much lemonade versus how many limeades to make, and you have this much sugar and this many cups, there is a correct amount of lemonade and a correct amount of limeade to maximize your lemonade stand. And I'm sure every little kid does that math. Right? But in real life, of course, there's usually far more than two things you're trying to work with to put constraints on. Right? Donut Bank really has to decide each day how many apple fritters, how many crullers, how many elephant ears, how many glazed donuts, how many fondant cookies, all these products, right? And they have to, they have this many pounds of flour. They have this much time in the fryer. They have this many hours of labor. There are all these constraints, right? I mean, if every donut takes this much time, and you'll only have this many man hours, etc. If you had three variables, we could write a system like let's say x1, x2, x3, and we have all these constraints and so on it, and we could actually do this. Now, x1 plus x2 plus 3 has to be less than this, etc. These are inequalities in 3 dimensions. The boundary of them is a plane, and then the colored in area, instead of being an area on a piece of paper, it's the volume on one side of that plane. Okay, so the bounded area after you had all these inequalities, it's sort of a weird, complicated prism, pyramid, complicated polygon. That's really hard to draw. And after 3, it's not even possible. After three variables. Because suddenly you're trying to draw something in 4 dimensions and stuff like that. It's not even possible. But the same technique would work if you just knew where the damn corners were of those polygons, of those polyhedra, to use the right word, in higher and higher dimensions. You could then plug them in and find the right value of z. Way back yonder, in World War II sometime, somebody figured this all out. His name's in the book. I'm not going to get stressed about that right now. What did I do with that? Oh, here it is. And he eventually got a Nobel Prize for it. But he figured this trick out, and he figured out that a nifty little short... Why was he doing it during World War II? He was trying to figure out how to optimize delivery of supplies to the front. Logistics. How do you get enough... You got this much room on the trucks. You need ammunition, you need food, you need fresh water, you need medicine. How do you... the total amount can't exceed this. The truck can't carry this much weight. We only have this many trucks. How do you figure out what's the correct... And it doesn't do any good. You can't take negative amounts of medicine to the front line. You can't take negative amounts of food. And he's the guy who figured all this out. In fact, it says it his name up there here. George Danzig in 1947. After World War II. Anyway, it was in World War II that he came up with his problems. And the technique he invented is the so-called simplex method. It is the same thing we've been doing, except since we can't actually do things on a graph anymore because these have too many variables in them and we can't draw it, we're going to do it using matrices instead. The simplex method is really, really cool and solves really interesting problems that real businesses are solving literally every morning. Okay? They probably have an app or a consulting firm or something that tells them. I doubt someone at Donut Bank is actually solving a simplex matrix. But in practice, they have some app or something that's telling them, okay, what do you have in inventory? We have this much flour, we have this much we got 8 hours of people scheduled to work the fryer, we've got this, how can we figure out what's the right amount of stuff to make? Or they're just guessing. And lots of businesses just guess. You know how you can identify the ones, Andrew, that just guess? The out of business sign. Right? Because they're leaving money on the table. Right? If you don't make the correct amount of stuff, you're throwing donuts in the dumpster. Meanwhile, other people who wanted to buy crullers, there wasn't enough of them. Right? Or the person working the fryer, you had 8 hours of people scheduled to work on the fryer, but they only had 6 hours of work to do. Right? All of us, if you don't come up with ways to do this in an optimal way, you're just leaving money on the table. Normally, I'm not a big PowerPoint guy. But I feel like the way the book explains this in section 4.1 is not its best. So having something that everybody can have and hold that is, I'm not saying that what I did is its best either, but you know what I'm saying, like it will help, okay? That being said, the version of the PowerPoint that I have right here is missing a few details that I put on the PowerPoint. I made some few changes this morning and then forgot to upload it back to Google Drive. So the one you will get that I'll put on It's Learning and send you an email about or whatever has a few extra slides here and there, okay? Secondly, it will probably take us 3 days to get completely through how to do the simplex method. Today, all we're going to be doing is how to set the problem up. How to actually get from a big, complicated set of inequalities to these matrices. Because it's not entirely simple.
So does that mean we're going to have a homework set?
You will have a homework set today of just how to set up problems. Okay? You won't actually be solving anything. You won't even do the next step of how to solve. I'll get there. So you do have a set it up kind of problem. Alright. I hate PowerPoint slides that have a bunch of words on them. If you guys take meteorology next semester, I have a lot of PowerPoints in that class, but most of my PowerPoints are like, it's just a picture that's behind me while I'm talking, or it has a few words on there. But because I really want you to have this, like to have it to hold, you know, when you're doing the homework, like you can print it out, or you can have it on your screen or whatever, I'm a little more verbose than I would be comfortable with on the slides here, okay? Alright, so what we've been doing with this last assignment has been called linear programming. Linear programming is this way of solving problems that find the value of, so far it's just been x and y, but now it's going to be x1, x2, x3, all the way out to xn, where you are optimizing some objective function. In general, we're going to mostly spend on trying to find the maximum. We're trying to find the maximum value of z. Maybe that's the maximum revenue or the maximum profit or whatever. There are also minima problems where you're trying to minimize costs or something like that. But we'll get there. And what we did so far worked pretty great because there was only 2 variables. It also wasn't so bad because there weren't that many of those constraints, those inequalities. Even if there had only been 2 variables, you can well imagine that we could have put more and more inequalities and made this feasible region really complicated, where there were lots and lots of corners, right? And we know that the answer's at a corner, but I could have made as many corners as I felt like, right? So this could quickly have gotten really, really hard. And it gets more and more awful the more variables you add and the more constraints. And in the real world, real problems have lots of constraints and lots of variables. Those trucks in World War II had to decide how much, I mean, I'm saying ammunition, there's probably 18 different kinds of ammunition, each one of which you have to figure out how much to carry, how many trucks to use, how much fuel to put on, how much medicine. There's lots of variables. And this is what that dancing guy figured out, is you don't have to come up with this linear programming graphics. You can use what he called the simplex method. Don't look up the word simplex. Don't even let me catch you looking that word up. Simplex is a stupid word. It means something like whole. Not like whole, like as in complete. Can't be subdivided further or something like that. Oh, now she's going to look it up. I knew she would. I don't know how that relates to this method. I don't understand, but
I feel like when I look at simplex, it's like simple and complex.
Simple and complex. It could be. I don't know.
There's a paradox within like that one word.
You know, I think last year when I had this class, I think the students did go and try to look it up just to figure out why it's called the simplex method. But anyway, all right. So this is in practice, this is exactly what we were doing. Of looking at corners and making a feasible, tell me, simple, it means like whole, unitary, molecular.
Characterized by a single part.
A single part.
That's just...
Atomic. In the literal sense of the word atomic. Can't be divided further. I don't understand what that means in this case.
The etymology comes from sim, which is as one together with...
Together like symphony?
Plek, which means like fold or to plate.
That's not helping me. Anyway, it's called the simplex method. Simple yet complex. I like it. Good enough. All right. So here's the deal. we are going to, over the course of a few days, once we get this whole business of the simplex method figured out, we will be doing other ways of doing program problems, but everything we're doing now is a problem that is going to be in what's called standard maximum form. A standard maximum form problem is going to be about finding the maximum of an objective function over a region. So something like what we've been doing here, where we had to evaluate over an objective region, over a feasible region, we were trying to find which of the corners had the maximum value of the objective function. And in practice, on page 143 in the book, they actually give you a definition of what it means to be in standard maximum form. And this will, a week from now or so, become more important, because we'll have problems that are in standard minimum form and in non-standard form and things like that. So, but for now, the most important thing here is that the objective function is going to be maximized. We're looking for, like, what is the most money we can make at Donut Bank today? Or what is the most money we can make at our lemonade stand today? Okay, our objective function, we're trying to maximize it. It's also important that all the variables have to be non-negative. Now that tends to be the way all these problems are set up. You can't sell like a negative number of lemonade cups. You can't load a negative number of boxes on the UPS truck. It will be also necessary to be able to write the constraints. Now remember, we're giving up on the idea of x and y because we're going to run out of letters real fast. So we're going to start calling it x1, x2, x3, all the way up to xn. I don't know that any of them are all that complicated we do in this class. I mean, I think we might have a few that get as high as 5. In real life, it can be hundreds. The software that runs FedEx. Somebody last year was doing some Googling and found that the software that runs FedEx might have hundreds of these things. All right. And you can see how the constraints are going to work. I mean, something like x plus y is less than 10 would mean like 1x1 plus 1x2 is less than 10. Okay. So all your constraints will have to be, if they aren't already, they'll have to be rewritten to be in that form. All right. Again, we'll get there. But the inequality's direction will become important. I don't think there are any that this happens on this homework set. But in the future, if there turns out to be some constraints that are the other way around, like if we had said x plus y has to be greater than 10, there are things we can do. There are things you can do to flip the signs of an inequality. You learn that in like algebra. Okay? We aren't there yet, but it will happen. But like I said, I'm pretty sure in the first assignment or two, it never happens. Alright, so when you are given a problem, the first thing you have to do is make sure the problem is set up in standard maximum form. And that, in fact, happens on some of the first couple of problems that I'm going to give you today, where you have to rearrange things to get them into that standard maximum form. Now the next little voodoo. Inequalities are weird. Inequalities, like the ones that have the greater than, less than, or the greater than or equal to, and the less than or equal to, are weird. Mathematically, they're weird. You probably didn't love it when you had to learn about inequalities back in some class. I mean, don't get me wrong. 3 is greater than 2, no big deal. But you had equations like 2x plus y is greater than 5 is not a simple thing to work with. Lots of the things you know and love about algebra work just fine if we're talking 2x plus y is greater, I'm sorry, let's just say less than 5. But lots of the things don't. Okay? A lot of the tricks you know for solving an equation don't work when it's an inequality. Or you have to keep flipping the damn sign in the direction of the inequality and so on. We don't want to play that game. And here's the funny thing about inequalities. They can be turned into equations. Real quick, just so that we're using the words right. Do you see the difference? Inequalities are the ones that have these things in them. And equation is the ones that have these things in them, right? They got the equal signs. You can change an inequality to an equation by adding what mathematicians call a slack variable. See, here's the deal. If x1 plus x2 has to be less than 10, a good way to write that in fact might give you access to more tools, is to make it x1 plus x2 plus some slack variable equals 10. So like if x2 is 1 and if x1 is 1 and x2 is 1, well, 1 plus 1 is less than 10, but a lot of your tools don't work with that inequality. On the other hand, x1 is 1, x2 is 1, and slack variable is 8 equals 10, works just fine, and you've got the equal sign. Lots of things will work now that are happening behind the scenes of how the simplex method works. Okay? Like we can do things like put this into a matrix and add one row to another row, or take this one and we can swap these two. All those matrix things that we did in the last unit. All of a sudden, all those things are possible. Because it's just a damn equation, and we know all about equations. So this idea of a slack variable is actually kind of neat. It is the word slack in the sense that it takes up the slack. Whatever isn't being used by the other stuff. Okay?
So it's basically...
Andrew will do, we got a job to do. Andrew will do what he can do. Luke will do what he can do. And then I'll pick up the slack. Right? Together what they did was less than the total job, and I did the little bit that was left. Right? That is slack in that sense, not like they're slacking or something.
So it's basically whatever it would take, because like x1 being 1 and x2 being 2 makes the inequality true. It's whatever it
It's
would
what you
take.
need to finish it up. Yep.
Okay.
Because this is just going to, there isn't a way to do matrices with inequalities. Like all those tools, remember all the tools like Gauss-Jordan and inverse matrices and stuff like that? That was a really handy set of tools, but they don't work for inequalities. They work for equations. But now we have a way to take the same idea and rewrite it as an equation. Okay? And frankly, the slack is kind of interesting. If x1 is the number of pounds of flour we'll use making donuts, and x2 is the number of pounds of flour we're going to use making apple fritters, it's actually kind of interesting to know how much is left after we do that. The slack is not a negligible thing, right? It's actually something we kind of, how much do we have extra? It's actually something we probably need to know anyway. So this idea of a slack variable is not so stupid. We're going to be working throughout this PowerPoint on this particular, it happens to just be example 1 in the book. But this is a perfectly reasonable looking thing that I could have given you last time. Where I could have said in Desmos, plot these inequalities and get yourself a feasible region, and then count the corners, and find at every corner, compute the value of z, except for one thing. Desmos is not nuts about 3 dimensions. Right? In fact, there are ways to trick Desmos into giving you a plot in 3D, but it's not a simple thing. Because this is, a feasible region might be a big rectangle, it might be a big pyramid, it might be some kind of weird shape. Okay? But at one of its corners, at one of its vertices, it's going to have the maximum value of that objective function. Alright. So if we wanted to do this, our first step is to rewrite those 3 inequalities using slack variables. So what we're going to do, let's first ask ourselves, is this in standard maximum form? Alright, it says, remember our first thing in standard maximum form is the objective function is getting maximized. Yep. The second thing in our our standard maximum form was that x1 and x2 and x3 have to be positive numbers. And that was in fact one of the requirements there in example 1, is that they have to be non-negative. What does the word non-negative mean, Lisa? It means 0 counts okay too, right? One of your options could be to make no donuts, right? Okay. Non-negative means positive or 0. And the other requirement of being in standard maximum form is it had to be something x1 plus something x2 plus something x3 is less than or equal to something. And we did it. Okay, so we're happy. This isn't standard maximum form. Okay, again, I can't remember if on the first homework set we ever get ourselves into trouble of that. But
What would we do
watch.
if we get ourselves into trouble with that?
Well, then we would have to do. That's why I think that's where we're going to have this come up in a later, like section 4.3 or something. Well, we're going to have to do things like multiply through by a negative number or something like that, so we can flip the direction of inequalities or something like that. I don't remember exactly all the details. So, when we take this and we are going to change these inequalities into equations so that we can do something with this, with matrices and stuff like that, it's going to take, well, we have 3 inequalities. Each one takes a slack variable to add to this so that it comes, see, I just took the same damn equation, but instead of an inequality, I just added slack variable 1. And now instead of being less than or equal to 150, it's equal to 150. And the second equation was originally an inequality, 2x1 minus 2x2 minus 8x3. It was originally less than or equal to 200, but now if I just add some slack variable to it, it's equal to 200. So now I've got S2 as a second slack variable. Slack variables often are going to turn out to be 0. It's often going to turn out to be the case that the correct answer is to have no slack. Use all the flour to make donuts. Or use all the sugar. The amount of slack 2 might be the number of cups of sugar left after you make this. It might very well be that the plan is use it all. That's how you get to your maximum amount of money. Okay? Slack variable 3 comes from our third inequality. 2x1 plus 3x2 plus x3 used to be less than or equal to 320. Now it's going to be equal to 320 because we're adding a slack variable to it. Again, all kinds of things become possible because we switch this to an equation instead of an inequality. Mr. Danzig was very, very smart about this. Hold on just a second here. Yes. All right. So, we have taken that same equation, that same set of inequalities, to change them into equations. Where we still have x1, x2, and x3 have to be positive. For what it's worth, the slack has to all be positive too. Okay? You can't have a negative amount of flour left over. Again, that would be a really slick thing, right? But that doesn't work. You can't have a negative amount of medicine on the truck. All right. A negative amount of medicine left at the warehouse, I guess it would be. Right? You can't let that in there. All right. So what did that do for us? It took a big system of inequalities, which we can't do diddly squat with. Oh, when there was 2, and it was just a happy little area on a graph, it wasn't such a big deal. But once it's more than that, you can't even really draw it. And change it into a system of equations that we have tools to do something with. Now, that being said, it's still not going to be happy. Because we have more variables than equations. If I go back over here, I want to show you something. It is not for nothing that I have many times used the same expression. Where I have said, look, we've got 3 variables and 3 unknowns. Or we've got 2 variables and 2 unknowns. Having the same number of variables and number of unknowns is what we do 99% of the time in math classes, because that means there's an answer. When you have 2 variables and 2 unknowns, most of the time there is an answer. Unless it's something crazy like, the 2 lines don't cross or something. There's weird possibilities. But by and large, that's why there's 3 equations and 3 unknowns. Or God forbid, 5 equations and 5 unknowns or whatever. Notice what we've got here. We've got 3 equations in 6 variables. Which we don't care for. What that tells us is that there might not be any solutions. For example, maybe it's not feasible at all. Maybe there is no feasible region at all. Now, generally speaking, that doesn't happen in the real world. There's always some number of donuts and some number of apple fritters they can make, right? But I mean, one can mathematically write a problem where Even making one donut takes more flour than you got, right? Or, well, how many hours do you have on the fryer today? 0. So the total number of hours you can spend on the fryer is 0. Well, guess what? There's no feasible region. Okay, that can happen over here. But most of the time, those aren't the interesting problems. The other possibility is there could be an infinite number of solutions. Well, that's in fact what happens when you have that feasible region, right? Any place in there would work. It's just only one of them's the best. In practice, that's what's going to happen most of the time, is that we'll have, in this case, 6 variables and 3 equations. We actually end up with, in this case, more variables than equations. There are tools, but it's not going to be easy. Alright, so what are we going to do? Well, it's not for nothing, to use that same expression again, that we do this right after learning about matrices. We're going to put these equations into a type of matrix. Hi.
Howdy.
Who are you looking for?
Kyle.
He's not in this class.
Lisa.
Lisa is.
Lucas.
He's not.
Logan.
He's not.
Okay, that's it.
Do you need Lisa?
I need Lisa. It'll be a quick one.
Okay. Somebody whistling taps over here. That's funny. Alright, if it's a quick one, we'll chill out for a minute. Alright. Well, let's talk more abstractly. We have made, if this was 6 equations and 6 unknowns, we'd have a tool to do this. I would not want you, MJ would fling herself in front of a bus before she would solve 6 equations and 6 variables with Gauss-Jordan, right?
I fling myself in front of the bus for 4.
Gauss-Jordan is nobody's favorite. But there's like the inverse matrix way, and there are others. If it were 6 variables and 6 unknowns, we would just have a way to do this. But it's not. It's more variables than equations. But let's at least get it into something like a matrix. This is, because it's not exactly the same thing as solving this in a matrix, Mr. Danzig, or Dr. Danzig, I don't know what his title was, came up with this word tableau instead, or tableau. Let's make it simpler. Let's say tableau. Okay. Meaning like table, or pose. It's closer to pose in this sense, but whatever. Okay. We're posing the problem. And what we're going to do is we're going to make each of our new equations with the slack variables and everything one row of the tableau. So I'm going to take, like for example, my first equation here that is was originally my constraint or whatever. Okay, my first column will be like the x1s, my second column will be like the x2s, my third column will be the x3s, my fourth column will be the slack variable 1. I'm going to later need a slack variable 2, but this equation doesn't have one. I mean, it's 0 times s2, 0 times s3. There's no z in this equation either, and it's going to be equal to 150.
I'm very angry right now.
Why are you angry?
Because if you look at the bit where S1, S2, and S0, it makes an identity matrix.
It will. It will indeed. She said that it was going to make, there's going to be a little bit of an identity matrix in there. So see how I took the coefficients from the first, this started off as being some kind of inequality. 2x1 plus x2 plus x3 was less than or equal to 150. We popped the slack variable in there so that we could make this an equation, so at least we had some tools to do something with. And then made it as a matrix form. Alright, we just put these little headings up here at the top to help us. We'll later make this look more like a matrix. We can do the same thing then for the second equation, where it was 2x1 plus 2x2 plus 8x3. Well, there's no s1 here, so 0s1 plus 1s2. Well, there's no s3 in this one, so that's no good. There's no z in this one, equals 200. It's a type of augmented matrix, but you get the idea. It's kind of a table isn't a bad way to think about it. A way of posing the problems is a way to think about it. Okay, we can put the third one in there as well. 2x1 plus 3x2 plus 1x3 plus 0x1 plus 0 times slack variable 2 plus 1 times slack variable 3 plus 0 times z equals 320. And in there too, we got to get this guy. He's our equation that we are maximizing. Okay, he's the only one that's got a z in it, for one thing. He's got to be rearranged so that he's in a similar kind of form as these guys were, where everything's on one side and the other side is just a number. So, like, we're going to pull this over here and make that negative 3x1. We'll pull this one over here and make it negative 2x2. I'll pull this one over here and make that negative x3. So, negative 3x1 minus 2x2 minus 3x3 plus z equals, in this case, 0. And then we'll just populate that last row. Yeah?
Does it matter if C is like positive or not? Or is
it would always be positive, because it's always going to be coming from an equation that z equals something.
No, but what I'm saying is, like, could you just subtract the Z, or is that like
You know what? I think you do have to do it this way.
Okay.
Yep. Yeah, no, you see what she was saying? Wouldn't it have been easier to move the z over to this side? I think we can't let this guy be a 0, but I mean a negative number, but you'll see. You'll see. Alright. Part of how this technique, when we get to like the third day of learning about it, part of the way that we'll know when things are going wrong is there's places that can't be negative. Like the whole last column can never be negative. So if something, you'll immediately know something went wrong if one of your last part of your last column was negative. Alright? So we'll pop those last ones in there, right? Here's negative 3, negative 2, negative 1, 0, 0, 0, 1, 0. Alright. PowerPoint made me a little table there. But that doesn't really look that much like a matrix. Well, the right word is this is a simplex tableau. And you'll see in just a little bit that it is an answer. The answer of what is a possible way to solve this system of equations. Let's say those system of equations and inequalities are describing the amount of donuts, fritters, and cookies to make in Donut Bank this morning. One of the possible feasible answers is already on this table. It's not the one that makes the most money, but it's on there. You just don't know how to read it yet, but we'll get there. But first off, let's make this thing look a little bit more like a matrix. Okay, let's wipe the little colors off there that were helping us. And usually what we do is they draw these two lines on there that separate off the bottom row. Remember that bottom row came from our objective function? And separate off that last column, because that last column was like on the other side of the equal signs. So George Danzig kind of came up with this notation. But I mean, other than that, we just put matrix symbols around the outside and stuff like that. It's kind of a matrix. Who's chuckling back there? Is that Lisa?
Yeah.
Lisa, you're going to love this.
Yeah.
I think you're going to feel really comfortable with this.
I feel like I looked up the definition of Tableau, and it says that it's a vivid or graphic description.
Well, or a graphic as, yeah, okay.
I'm wondering what that has.
Tableau, it's the same stem from which we get table, it's the same stem from which we get, I usually think of the word tableau as meaning more like pose. But it is also like as a table, as in like a table. I don't know.
It's French for board. Wow.
For what?
Board.
Board?
Yeah, like,
Okay. Probably from like the top of a table.
Yeah.
Alright, anyway, it's a tableau. Think of it as you're being fancy about the word table. It would be fine.
Can you pronounce it like
Tableau. Let's honor the French. Tableau. No, a tableau will be fine. Okay. So, alright. Let me fling some vocabulary at you. On the bottom row here, the ones south of that little line that we just drew, the ones that came from the objective function are called the indicator variables. They're going to be super important when we start doing things to this matrix. Now, on the version that I'm going to post on It's Learning, I found a mistake here. The color yellow, notice, doesn't extend all the way. They're not all indicator variables. That last one isn't an indicator variable. And I have a mistake here. I was drawing the colors and I didn't realize I went too far. This one isn't either. The indicator variables are just the original variables and the slack variables. Z isn't considered an indicator variable either.
So not Z.
Not the Z either. But I'll have that corrected on the PowerPoint that I post. But that, I did literally like 10 minutes before class, I changed that on the PowerPoint and then forgot to post it. So that I could have it. So it's sitting there on my machine. So that's an important word. When we start learning the simplex method, when we actually start doing something to this matrix, like multiplying this row by this row and that kind of thing, we're watching what happens to the indicator variables. As we make things happen, they will be changing, and when they get to a certain way, that is how we'll know we're at the optimal solution. Okay? You know how when you multiply like this row by this row and so on, numbers were changing all over the place? Every time you do things to this matrix, those numbers are going to change, and we're waiting for things like them all to be positive. Okay? We're just not there yet. But watch those indicator variables. Here's a harder word. Any column in this table where everything is 0 except for one value is called a basic variable. So like in this case, slack variable 1 is a basic variable. Right at this moment, he has zeros everywhere except for, in this case, the first column, the first row. So at this stage of the problem, slack variable 1 is a basic variable. I don't know what the sense of the word basic here is. Basic means lots of very different things. I don't think it means as in it's fundamental. I think it has to do with the fact that it is part of, okay, don't look it up, don't look it up. I thought you were grabbing your phone. No, that's all right, that's all right. No, I think it is the adjectival form of the word basis. And I think that I believe that the basis of a system of equations is a thing you may have learned about in like this Webster's class at some point and completely forgotten. I know I've forgotten about it. I think that the word basic is the adjective form of the word basis in this equation, but I could be wrong. So it is the variable that's forming the basis in a algebra 1 sense. But we will never see that. We don't care. We're just using the word basic and non-basic. Okay? So like in this case, slack variable 1, at this moment, in this form of the simplex tableau, we haven't done anything, we're multiplying any rows or anything like that yet. S1 is a slack variable 1 is a basic variable. For that matter, so is slack variable 2, and so is slack variable 3. At this step of the problem, those are the basic variables.
Couldn't see it.
You know, I didn't highlight it because I don't know if that counts. Hold on. I didn't have the book with me when I was writing this here. Basic variables. No, apparently... Get a unique feasible solution to be identified. If there are m equations, then they're going to be... It does not expressly say... Here's the deal. If you look at page 146, it does not say z can't be a basic variable. On the other hand, it highlighted the basic variables in this problem. And z looks like it would be fine, and yet it isn't counting. Like it's not highlighted. So I don't think the z variable can be a basic variable. But I have to admit, I wondered the same thing when I was making this PowerPoint and fixing this PowerPoint and so on. But right now, I would definitely say slack variable 1, 2, and 3 are the basic variables, and x1, x2, and x3 are the non-basic variables. Now, that will change. You can even kind of start seeing how it will change. If we do something like replace row 3 with row 1 plus row 2, row 1 plus row 3, because we're going to be doing row operations just like we did. We're not doing that today. I think that's Monday. But when we get there, you can see what's going to happen, right? Just like when we were doing things like Gauss-Jordan or finding the inverse of a matrix by hand, you know, once we add row 1 and row 3 here, what's going to happen to this variable? It's going to become 1 plus 0 is 1. Well, if this is replaced, then this one isn't basic anymore, right? Because now it's got two variables in it that are, two entries in it that are non-zero. So, but on the other hand, if we plan this right, maybe we're making something else basic by doing that. Okay? Like, for example, maybe we are taking this row minus this row. Well, that'll make this a 0, but then this one minus this one will change this one to a 1. But you know, maybe we made something else basic by having done that. When each step along the way, when we do this, we will get a non-zero, we'll be making a different variable basic. Now here is the astonishing thing that's as far as you're going to get today. As long as you've made no mistakes setting the whole thing up, this initial simplex tableau, as well as any tableau you get in the future, as long as you follow the rules, is a solution. This is a perfectly good, you don't know yet, I'm going to show you how to read it off of here, but a perfectly good answer to how many glazed donuts, apple fritters, and cookies to make, or how many boxes of medicine, ammunition, and food to put on the truck, or whatever. As long as the tableau is, you haven't made any mistakes, it is an answer. It just isn't yet the best answer. But let me show you how you could pick the answer off this one. Okay? The answer involves having to keep track of which ones are slack variables and which ones are non-slack. Now, on the version of the PowerPoint that you will have on It's Learning, I've made it a little more clear by putting in like 48-point font down here at the bottom, letters about yay tall, how to read a solution off a simplex tableau. Okay? So it's clear what's going on this next string of slides here. What you do is you take one of the columns that is a basic variable, and you find the entry in it that is the non-zero one, like this case right here. Okay? Great. That row is important then. The row from which, in the basic variable, that's where the non-zero happened. In your book, no, they don't yet. Later they'll have this more cleverly explained. They'll have like an algorithm kind of thing, like a flow chart to help you with this. Maybe we'll build something like that on Monday. All right. You found you found a basic variable. You found the entry in there that is non-zero, and you picked its row. All right. Those are the numbers we're working with right now. Now, any place in there on that row where we're talking about a non-basic variable, just cross it out and replace it with 0. So, like this was a 2, I don't give a damn, it's a 0. This was a 1, I think, I don't care, it's a 0. This was a 1, I don't care anymore, it's a 0. This is a basic variable, alright, I do care about its answer, but it happens to be 0. This is a basic variable, I don't care because it's a 0, equals 150. So 1 times S1 equals 150. So one solution involves whatever slack variable 1 is, it's 150. Okay? Now let's pick another column. Here's another basic variable. Right? He's got all zeros except for this thing. Take the column he's in. This wouldn't have to be a 1, by the way. After we've done some other operations, this might not be a 1, but we'll get there. Alright? So anything that is non-basic, cross it out for now. 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times slack variable 1 plus 1 times slack variable 2 plus 0 times slack variable 3 plus 0 times z equals 200. So in another solution, slack variable 2 is equal to 200. Hey, if you actually start looking down here at like this equation right here, if slack variable 2 is 200, what is x1 and x2 and x3 going to be? I mean, one serious possibility starts looking like this is 0, like x1 is 0, x2 is 0, x3. Is that a solution? Sure. A perfectly good solution could be make no donuts, no apple fritters, and no cookies today. That's a solution. That is a feasible solution. Is it your best solution? Probably not. Okay? Alright? Do the same thing for another basic variable. Here's a basic variable. It's all zeros except for one place. Highlight its column. Alright, this is non-basic, right? It's full of other stuff, so its value becomes a 0. 0, 0, 0, 0. 1 times S3 plus 0 is 320. So S3 is apparently 320. Which again, you look over here, and in fact, at no place along the way did we ever put a value in x1, x2, x3. In this case, x1, x2, and x3 are all 0. We made no cookies, no apple fritters, and no donuts. That is a feasible solution. With slack of we left behind 150 cups of sugar, 200 cups of flour, and 320 hours of time in the fryer, or something, whatever this problem was. Okay? It is a solution. Is it the best solution? Of course not. We'll have to do something to this, but we were able to pick a solution off of here. That is as far as this assignment goes, where you start getting practice picking the solution off. Okay? We will then later be doing things. Oh, I just highlighted it here. So if I flipped back, I like that trick. If I kind of look back to an earlier slide back here and looked at these inequalities, it was actually perfectly fine. No donuts plus no apple fritters plus no cookies is less than 150. And no is less than 200, and no is less than 320. It's a perfectly good solution. Is it optimal? Of course it's not optimal.
I mean, if you're having a bad day.
Yes, maybe it is not. By the way, this is why businesses sometimes make weird decisions. Or seems like weird. For example, do you know how much aluminum they want to make over at Alcoa? The optimal amount of aluminum to make is 0. Over the Alcoa, the works, they plug this in. The correct amount of aluminum to make each day is 0. Make no cans, make no aluminum I-beams, and make no aluminum foil. Do you know why? They make more money selling the electricity that they have a contract on than they do selling the aluminum cans they made with the electricity. The Alcoa plant in Warwick County is really an electricity vendor.
Yeah.
Yeah, the union requires that they still have some pot work and some, whatever, so there's a minimum amount of work still done there, but they actually make more money selling the electricity than they do the cans.
My house is run off of Alcoa.
Yeah. They have a huge, they have long-term contracts for 40 years to get at least this many megawatts of power at any given time, and they make more money selling the power than they do selling the aluminum can. Okay? But they also apparently make more money not buying the union out of their contracts and stuff like that. So whatever the minimum, if the union says there's got to be 10 people working in the pot room and 5 people working in the machine shop, they do it. Okay, it's apparently cheaper to keep them there than to make some. But they used to, of course, be the aluminum company of the Americas, right? I mean, they used to, but they don't anymore. They're now the electric vendor. There's a number of companies that are that kind of way. The correct solutions, in fact, don't make anything.
I mean, one of the things could be is that it's prices are high for flour, sugar, and eggs.
Sure,
so
sure.
You want to wait, and then the prices are going to drop tomorrow.
Maybe if your constraints were those things are high, but you can rent the front room of Donut Bike out for a birthday party. It might make more sense. Don't make any, so that you don't have people coming through. Don't make any donuts, apple fritters, and cookies, and just let them and make $200 by having a birthday party in the front room. That might be. It might be. The right answer is don't make any cupcakes and stuff like that.
You can make this very complicated.
By the way, notice something magic happened. Down here in the bottom, alright, if we know this thing is, it's non-basic, it's 0, this is non-basic, it's 0, this is non-basic, it's 0. Well, S1 and S2 and S3 are something, but we're multiplying them by 0. 0 times S1 plus 0 times S2 plus 0 times S3 plus 1 times Z equals 0. So Z equals 1 times Z, Z equals 0. Hey, but we knew that, right? Our objective function was, how much money we were making was 3 times this plus 2 times this plus 1 times this. We know it's 0. Then really, the answer is just right down here. Can you imagine how clever that George Danzig must have been? Alright. You can generally then read, again, I don't normally put so much verbiage on a slide. I don't like these wordy slides, but I wanted you to have something at home. You can, in general, then always pick an answer off a matrix tableau. As long as you've made no mistakes, an answer is there. It just, in general, won't be your useful answer. To make it useful, we have to get to one of the optimal corners. And in order to do that, we have to use a process called pivoting. And pivoting is what we will learn on Monday. But pivoting is just row operations. Yes?
Hypothetically, if you set up your Tableau and stuff, and it's you could see where it would make an identity matrix in the problem, but it's not lined up correctly. Could you like flip the rows? Like say where S3 would be is where like the S3 row where that one should be is S2 and then S2 is like S3.
I don't know if it would help. Here's the deal. The book actually says don't go around moving one row to another row. I think the only reason why they care is because they don't want you to accidentally get, the indicators do something different. And they don't want you to think, oh, I just swapped this one over here with those indicators, that bottom row, then we could do, no, because the indicators are playing a different role in this process, okay? We haven't gotten there yet. But I think more importantly, it just doesn't end up helping anything to do the flipping of the rows. Okay? Book says don't. Okay? Alright, we are not going to learn how to pivot today. But pivot is a process where you are either told a particular row and column, like this entry right, let me just back up to where there's a tableau. Let's just say that in the first set of problems, which will happen on Monday, they'll say pivot it on this variable. Okay, so they'll say this one, they'll actually have highlighted it. And then there's a way that you like multiply this row times this row, or take this row minus this row, or something like that, and things happen. Okay? And if you do it right, the new row pivot matrix after you pivot will be also a solution, and you could read a solution off of it. And if you pivot a few times and get yourself to a place where certain things are happening, like I think all these variables are positive, then you have pivoted to the optimal solution. But we're not there yet. So here's the deal. We're not going to learn to pivot today. It's too much. So, for today, all your problems involve is just setting things up. That is not it. That is not it. There we go. Let me just put this up and blow up the size of this. I don't have it available to you in another form just yet. But there's only a handful of problems. Oh, wait, that's pre-calc. That's not you.
Start.
Hold on. Oh, crap, I don't have those dudes for pre-calc that they're making fun of.
What thing?
Those little slips of paper, they were mocking me about that the other day in study hall.
Yeah.
I am just about tired of excuses for people, I didn't write the assignment down. Well, then guess what? You're getting a little piece of paper. Except apparently today because I forgot to copy it.
Yeah.
Alright.
That class will have an excuse for everything.
Yes, they will. And I am pretty thick-skinned. Oh, look. There aren't even all that many problems. Here, blow it up. 148, 1 through 4. And if you look at 1 through 4, there's not that much to it. And then 5 through 8, you only have to do part C. And then 9 through 11 is writing in the initial tableau. And then 15 and 16. 15 and 16 are the only two where you actually are reading a solution off of the matrix, off of the tableau. All right. Now,
You want our homework?
I do. And I also am going to send you, I'm just going to send it to you for right now instead of putting this on a, on that starting females page. I'm just going to send you the link, okay? Let me just do that because that's faster. It's just been a day.
Yes,
I mean, Lisa was in trouble. Good Lord.
I mean, I wasn't in trouble.
I know, I apologize if I just embarrassed you because I had no idea what that was about.
It's okay. I'm not embarrassed.
Should you?
No.
Alright, there's only 2 questions on the exit ticket, and I intend to be friendly about it. I mean, we just saw this stuff. Actually, some of it's more from the last assignment, but that's another story. Alright, Andrew.
When do the points due for getting points back on the test?
Let's begin Monday.
For test?
Yeah.
Thank God.
Oh, that's what I
You guys didn't show me? Thanks. What did you say?
I said that's what I forgot to do.
Sorry, you got some homework for me, or you said it all? You said it all. You said it all. Alright. I wonder if I have enough email that I'm behind. Alright, so this goes into, I'm so much more organized now. Now all the stuff that I have done is now organized in a folder, which will still not get done, but whatever. This is Finite Math 2 grade, and it goes in this spot. And I've got Luis's. Luis needs to show her work. Homework. Luis is in pre-calc 2 grade. And we're going to stop the recorder.